Welcome. That's a mass on an inclined plane, and then figuring. Let's draw an inclined plane. Let me do it. And we don't want to deal with friction.
No, so I will assume the inclined plane is made out of ice. It has no friction. Frictionless ice. Oil on ice. So that's, let me just draw this nice looking inclined plane. There you go. Draw the base of the plane. So it's like a wedge. Whoops. Okay. And let's say that I have a block on this inclined plane, and I'll make the block purple. Like that. I should probably draw this ahead of time, but that's okay. Gives my mind time to think of what I'm going to do next. So I have a block on an inclined plane, and let's say that this block is 10 kilograms. 10 kilograms. And for simplicity's sake, I'll assume that the acceleration of gravity is, instead of 9.8 meters per second squared, so acceleration of gravity, instead of saying it's 9.8 meters per second squared, I'm going to say that that's approximately 10 meters per second squared. And I'm going to do that in general in all of the physics videos, just because it makes the math easy and we don't have to get a calculator out. So my question to you is, what is going to happen? And you could guess intuitively. We have a block on the side of this, I guess, wedge of ice. It's naturally going to fall down the ice, right? It's going to slide down this side of the ice. So it's going to move in this general direction. But my question to you is, how fast is it going to move in that direction? And more importantly, how fast is it going to accelerate in that direction? And it would accelerate, right? Like anything falling down a hill or sliding down a hill, as it slides, it gets faster and faster. So let's try to figure this out. We already know what would happen if there was no wedge and the thing would just drop. It would accelerate at the acceleration of gravity at 10 meters per second squared, roughly, or 9.8 meters per second. So what's happening here? So this is going to turn into just pretty much what we've been doing in every video so far. We're going to say, well, what are the forces acting on it? And then we're going to break up that force vector into its component vectors to see how it acts in the various directions. So what is the only force acting on this? Well, actually, there are several forces, but what is the force that's pulling down on this mass? Well, and that's the force of gravity. And so I will draw that. So the force of gravity is pulling in what direction? Right, straight down. So this is the force of gravity. So let's say the force of gravity is that. That's the force of gravity. It's pulling straight down on that block. And what is the magnitude of the force of gravity? Well, it's going to be the mass times the acceleration. So 10 kilograms times 10 meters per second squared. I mean, it really is 9.8. So it's roughly 100 newtons. So this is the force of gravity. So this is the force of gravity. Force of gravity. And we know that the force of gravity on this block is 100 newtons. Another way of saying it, this block weighs 100 newtons. But the force of the block is going downwards. And what we want to do is we want to figure out how fast is this block accelerating in this direction. And also, later on when we do friction, we also want to know, well, how much of this force of gravity is actually, what's its component that's pushing downward on the wedge? Because once we start doing friction, that matters a lot in terms of how much are you pressing onto the surface. So what I'm going to do is I'm going to break up this force vector into its two components. One is the normal, the component of the force vector normal to the plane, and normal just means perpendicular, if you've learned that already in algebra. And let me draw that. So that would be, let me pick a good color. Let's say green. So this is the normal force. This would be the component. This would be the component that is perpendicular to the plane. Right? It's perpendicular. Right there. And then the component of the gravitational vector, that's parallel to the plane, I could draw it here, but instead I'm going to shift it down here so we get a nice triangle like we're used to dealing with. So let me draw it here. So then we have, so the component that's parallel to the plane is here. So I don't know, let's call this, I actually forget what the convention is for what they call the force that's parallel to the plane, or that's kind of in the direction that the mass is accelerating. But I'll just call that the force parallel. Force parallel. And of course, the green, this is the normal force.
And so if to figure the force parallel and the normal force, we essentially just have to figure out what this angle is right here. And I'll do that in this color. We have to figure out what this angle right here is. And I'll call that angle alpha. And what I'm about to show you is that this angle alpha is actually the same angle as this angle right here, which is the angle of the plane. And it might not be obvious at first, but I'll do a little mini proof here, and in the process I'll probably clutter the picture, but you'll bear with me. This right here, this is a 90-degree angle, right? If we drew a line from this point down to, going up and straight down, right? And so this would right here, this little brown angle right here, what would it be? It would be 180 minus 90 minus alpha, right? So 180 minus 90 is 90, so 90 minus alpha. And 90 minus alpha, you probably can't see that, but just take my word for it. That says 90 minus alpha. And we know that this angle, this brown angle, plus this blue plus this blue angle have to equal 90 degrees, right? Because this whole angle right here, this whole angle is 90 degrees, because this one is also 90 degrees. Hopefully that makes a little sense to you. So if this is 90 minus alpha, and this angle is alpha, and if they add up to 90, or I think I'm talking in circles, then this has to be alpha. And you could just add them up, right? 90 minus alpha plus alpha, this whole thing is 90 degrees. So I just proved to you that this angle is equivalent to this angle. And that's actually a big thing to prove, because now we can, if I were to tell you the angle of this inclined plane, or any inclined plane, you can figure out what component of the force of gravity is normal to the plane, so it's kind of going straight into the plane, perpendicular to the plane, and what component of the force of gravity is going parallel to the plane. So let's do that. Let's say that this inclined plane is at a 30-degree angle, right? So that this angle right here is also going to be at a 30-degree angle. And if that proof didn't make much sense to you, or maybe it made sense to you, but it doesn't make intuitive sense, just imagine a bunch of different planes of various steepnesses, and then what would happen to this angle, right? What is the difference between the normal force and the force of gravity? You can imagine, if you have a very high, well, I won't draw it here because I don't want it to waste too much space, but maybe I'll do it in the next video, give you a little bit of an intuition. But anyway, if this is 30 degrees, what is the force that's parallel to the direction that it's sliding, essentially? What is this angle right here? So we know the hypotenuse, which is the force of gravity, right? We know the hypotenuse, and we know the opposite side, right? Opposite of the angle. So the opposite over the hypotenuse is force parallel over force of gravity, right? Opposite over hypotenuse, and that's sine, right? SOHCAHTOA. Sine is opposite over hypotenuse. So that equals the sine of 30 degrees. The sine of 30 degrees. Or we could solve, we could say the force parallel. I don't know if P is a good letter to use, because you could also confuse it with perpendicular. But let's say it's P for parallel. So the force parallel is equal to the force of gravity times the sine of 30. Sine of 30 degrees. And so the force parallel is equal to, what's the force of gravity? We already figured it out. It's 100 newtons, right? 100 newtons. That's essentially just the weight of the block. And what's the sine of 30 degrees? We've done that enough times, so that's times 1/2. So the force parallel is equal, sorry, I said P parallel. No, the force parallel is equal to 100 newtons times 1/2 is 50 newtons. So we're almost done. The component of the gravitational vector that's going parallel to this, that's going parallel to the surface of the plane, is 50 newtons, right? So if essentially there's a force pulling at 50 newtons on this block in this direction, how fast will it be accelerating in that direction? Well, F equals ma. F equals ma. So we could say force in the parallel direction is equal to mass times acceleration in the parallel direction. So 50 newtons is equal to 10 kilograms times the acceleration in the parallel direction. So divide both sides by 10, and you get the acceleration in the parallel direction is 50 divided by 10, 5 meters per second squared. So roughly, this thing will accelerate in this way, roughly at half the rate at which it would naturally fall if this inclined plane wasn't there. So hopefully that gives you a little bit of intuition, and in the next video, maybe I'll introduce friction, and we'll actually use this normal force. I'll see you soon.